It's difficult to measure the amplitude of a very low amplitude signal. There's a couple of problems with this. One is that it's noisy, and the other is that the signal jumps around. You can't trigger the scope. So even changing the triggering knob on the scope up and down, I can't lock the signal into place. There are a couple of ways you can cure this. One way that sometimes works is to go to the trigger menu and then go to the coupling button over here, take it off of DC, and put it on a coupling setting that rejects high frequency. That would be the high frequency reject button over there. Then it turns out that you can probably trigger the scope. It's still jumping around a little bit and not going precisely back on top one signal on top of each other, but it's sort of okay. You can adjust the trigger knob. If I make the trigger too high, it's going to continue to jump around. But bringing it back into place gets me somewhat stable triggering. However, there's a better way of doing this. Very often, you're taking the signal off of the signal generator. And the signal generator has an output which is specifically designed to trigger scopes. It's called the trigger output. Let's take a look at what the signal is that's coming out of this trigger output. If I take a BNC cable and plug it into the scope, so here it comes into the scope, turn channel 2 on, you can see that the signal that we get from the signal output is big. It's about 8 volts tall, and it's exactly locked to the size of the wave function that's being put out. This means that it's excellent for triggering on. The scope is all set up to do this. All we have to do is to move the input to a special channel on the scope called the aux-in, or the auxiliary input, and plug this trigger signal into that input all the way over here. Then go to the trigger menu, and we can go back to DC, so it's free running, but what we're going to do is to change the source of the signal that the scope uses to trigger on from previously channel 1 now to this auxiliary input over here. To change that source, all we have to do is push on the source button and move the multi-purpose knob down to here to aux, and we're done. The signal is going to stay nicely triggered now, and it's not going to move around. That solves one of our problems. The signal is stationary and stable. But still, we've got a lot of noise on that signal. How do we measure it? Let's temporarily make the signal on the scope large. The signal is now big enough so that we have no trouble reading the size of the signal off of the scope itself. Let's say we want the peak-to-peak voltage of this signal. You can see that it's approximately 5 divisions, so it's about a 1 volt peak-to-peak signal. But the scope can read that peak-to-peak voltage all by itself. What we do is use the measuring functions on the scope. Go up to the top, push the measure button, and then add a measurement down here. There are many measurements that the scope can take, but one of them is going to be the peak-to-peak height. So let's add that measurement like this, and then you can see that down over here, it's telling us approximately what the peak-to-peak voltage is, about 1.07 in this case. Now that may or may not work for a large amplitude signal, but as you'll see in a minute, it doesn't work for a low amplitude signal. So now we're back on a low amplitude signal. It's fuzzy, but it's pretty obvious by looking that the signal goes from here to up over here, that the signal is about 2 divisions, and since we're on 10 millivolts per division, that's a 20 millivolt signal. And yet the peak-to-peak rating down here is about 80 millivolts. It has no bearing on reality. Why did that happen? Well, it's measuring the true peak-to-peak voltage, and that includes all of these fuzzy spikes that you can see, which extend above the waveform and below the waveform. You don't want to measure that. That's just noise. It shouldn't be there, but it's going to turn up on this measurement. And worse yet, if you look carefully at the scope, You can even see, if I move inwards, that there's some even finer noise, say, that you can see right over here. See this faint yellow? That finer noise is the background envelope, and it's picking up all of that. We certainly don't want to measure that, it's noise, and yet our automatic measurement is picking it up. So what do we do about that? Well, there's two things we can do. The first thing we can do is to add another measurement, a slightly different measurement. So let's go back to the measurement menu, add measurement, and take a look at the options. What we had used previously was the peak-to-peak measurement. You can see this dotted line over here is showing you that it's going from the extreme bottom to the extreme top. But let's try a different one. Let's move the knob up and look at what they call the amplitude measurement. This amplitude measurement has the dotted line kind of going through the bulk of the waveform, ignoring the stuff on top. Let's take a look and see what that does. So we'll add that measurement, and now take a look at this. The peak-to-peak voltage is ridiculous. It's 80, 90 millivolts. But the amplitude measurement is, or potentially correct, it's something around 20 millivolts or so. And that's what we got when we were doing this by hand. So it seems that this might possibly be just about what we want to do. But it's still noisy. So how do we improve on that? For a repetitive signal, there's a great way to improve the signal to noise, to get a much cleaner signal. And that's to use averaging. All of this noise is somewhat random. Sometimes the signal's high from the noise, sometimes it's low. If we average, we can get rid of this. And the scope has a way of averaging. What we do is go to the Acquire menu over here and simply turn averaging on. Turn averaging on over here, and now we're averaging 256 times. And as we do that, as time goes on, you can see the signal is getting cleaner and cleaner. It takes a while for it to acquire all of those 256 signals that we're averaging. We in fact don't have to average 256 signals. There are a bunch of different settings. We can, for instance, average only 8 signals together, and then we get a much faster response, but it's not as pretty. It's still got some noise on it. This works really well. If I set the averaging back up to 256, you can see that the amplitude setting now is getting quieter and quieter. In the end, the signal turns out to be about 23.6 millivolts. We can read this off of the amplitude, and we can also see it on the oscilloscope screen itself. Notice also that with averaging on, the peak-to-peak signal also cleaned up a little bit, but the amplitude measurement is still the better bet. So what's the bottom line? If you're trying to look at a small signal, the first thing you have to do is set up the triggering so that the signal is always repeating right over itself over and over again without any jitter, a stable triggering situation. Next, you can use an amplitude measurement rather than the peak-to-peak measurement to measure a peak-to-peak signal. The peak-to-peak signal measurement is just too susceptible to noise. Always use the amplitude measurement. And then you can turn off on averaging. And with averaging on, you can get a very nice, clean signal, which is going to be a very accurate measurement of what your signal is actually doing. Keep in mind, though, that averaging slows down the response of the scope. For instance, if I take away the signal altogether, nothing much seems to happen on the display. That's because it's averaging together the zero signal, which it's currently getting, with all of the previous signals that it had gotten before. And so that averages to a sine wave, albeit a sine wave that's very, very slowly decreasing in amplitude as it pulls in more of the zero samples. Well, I'm an impatient guy, and I can speed this up simply by clicking any of the settings. I can move one of the settings away from its original value and back to its original value. And that changing any setting immediately resets the average. So we go to 0. immediately. We don't have to wait for it to acquire 256 or somewhat more than 256 signals. Now, that works in the opposite direction. So for instance, if I plug the signal back in, you can see that it takes a long time for the signal to build up to its true amplitude, because now it's averaging in some of the zero signals along with the proper sine wave. Once again, I can speed this up simply by clicking the knob backwards and forwards, and I immediately get my proper signal. It takes a while for it to average back to zero, but there it is. Now, funky things can happen with this if you're not careful. For instance, if we change the frequency of the signal, at the moment we're at a 20 hertz signal, so let me change it to a 35 hertz signal over here and move back to here, then we get all sorts of distorted waveforms as it transitions from the proper signal to from the old signal to the new proper signal. It goes through, you can see these steady phrases. Once again, I'm impatient, so simply by clicking this knob backwards and forwards, I can immediately get a rendition of the proper signal. So, there are lots of tricks for getting a good signal, but one of the things you should always do is look at the scope yourself and make sure that any measured signal that you receive, like these two measured signals over here, is really a realistic number for what the signal actually is. It's easy enough to see that this is now 2 divisions over here, so that's going to be about a 40 millivolt signal, and confirm that this number that the scope is giving you directly is the proper number.